Welcome back to the deep dive. This is where we dive into some of the densest source material out there. We're talking advanced numerical analysis, specialized programming, you name it, and we pull out the most important nuggets of knowledge for you. We want to give you a real shortcut to being well informed. And today, we are really deep in the engine room of scientific computing. We're going to be grappling with a problem that I think haunts, well, pretty much every engineer, every quant, every machine learning researcher out there.
Oh, yeah. It's that fundamental challenge of floating point precision loss.
Exactly. I mean, if you've ever run a complex simulation, maybe for millions of iterations, only to watch it just drift into complete garbage because of rounding errors piling up, you know what we're talking about. You know the limits of standard computing.
It's so true. It's like the digital equivalent of trying to measure the distance to the moon with a ruler that's only marked in inches. I mean, your standard 64-bit double precision, which is, the workhorse of everything we do today, it gives you about 15, maybe 16 reliable decimal digits.
Which is fantastic for most things.
For most things, absolutely. But there are these crucial fields of the cosmology, certain kinds of financial modeling, even advanced cryptography, where that just isn't going to cut it. It's not even close. You need 30, 50, sometimes even 70 stable, guaranteed digits.
And that search for that guaranteed precision is what led us to our sources for today's deep dive, which all cover something called TLFloat. And this thing is, well, it's an absolute marvel of numerical engineering.
It really is. It's a C++ template library, and its whole job is to provide IE 754 compliant floating point operations.
But across this insane range of precision levels, right, it scales from these tiny 16-bit formats all the way up to this mind-boggling 256-bit octuple format.
And that's the goal. Our sources show that TLFloat is basically designed to be a precision shield. It's there to just eliminate the problem of precision loss, but for those very specific, highly specialized applications.
So our mission today for you is to give you that comprehensive look under the hood. We're going to look at the architecture, the specific engineering tricks they had to pull off to guarantee this precision, and this is the big one, the performance trade-offs you have to accept when you step beyond hardware-native math.
And that's so key, because the core promise, and this is what really makes it unique in my opinion, is that the library is built around this unified, templated core design.
Okay, so it's not just a patchwork, like different types all bolted together.
Not at all. It's a systematic, really consistent approach.
Yeah.
And that structure is what ensures that even these incredibly extended precision levels, we're talking quadruple, which is 128-bit, and octuple, 256-bit, fully, and I mean fully, comply with the IEEE 754 standard.
And that compliance is just non-negotiable, right?
It has to be. It's what guarantees that these custom software-defined types behave predictably. They handle all the special cases like NaN and Infinity exactly the way your hardware does. That consistency, well, that's the foundation of numerical trust.
Okay, let's unpack that architecture. Because from what I've seen, TLFloat is designed for, let's say, maximum flexibility, but also efficiency. When you look at the code, it's almost like a set of nested layers.
It is. It's a classic separation of concerns model. You really need that when you're trying to unify code that has to handle both tiny 16-bit types and these, 256-bit behemoths.
So at the top layer, the user-facing part, you have the TLFloat class template.
Right. That's what you, the user, would instantiate in your C++ code when you declare a high-precision number. It gives you the clean operator overloading all the familiar functions. It just works like you'd expect.
So that TLFloat class is the nice, clean interface. It's the wrapper, but it's not actually doing the heavy lifting itself.
No, it's not. It encapsulates something called the internal unpacked float template. And that is the true engine of the whole library.
The engine room.
That's where all the magic happens, yeah. The unpacked float template handles the actual floating point representation, the sign bit, the exponent, the mantissa, and crucially, it contains all the logic for the arithmetic. It defines the whole structure based on 4 template parameters.
And those 4 parameters are what let TLFloat customize the behavior for every single precision level, from 16 all the way to 256 bits.
Exactly. We're talking about the mantissa type itself, a required higher precision type for intermediate calculations. They call it longmant, and then the specific number of exponent bits and mantissa bits.
So that templated core is really the secret sauce for keeping it all in one unified code base.
It has to be. It means whether you're adding 2 16-bit numbers or 2 256-bit numbers, the fundamental logic flow is always the same.
What's that flow look like?
It's always.
Yeah.
Check for special cases, align the exponents, add the significance, normalize the result, and then do the final rounding. Only the underlying data types and the bit counts, which are defined by those template parameters, actually change.
And that unified approach lets them support this incredible spectrum of types. It covers pretty much every modern numerical need I can think of.
It's a full spectrum. I mean, of course, you have your standards. You have your 32-bit float, which gives you, what, about 7 decimal digits?
Yep. And 64-bit double, your standard, gives you 15 or 16 reliable digits.
But the real innovation here is at the extremes, both the really small end and the extremely large end.
Let's start small then. We have the 16-bit types, half and bfloat 16. We see these a lot in, say, GPU applications for memory or speed reasons.
Right. And then you jump to the other end of the scale to these massive high-precision types that just push numerical limits so far beyond what any native silicon can do. We're talking quadruple at 128-bit and octuple at 256-bit.
Okay, let's talk about quadruple precision. That's the first major leap.
It is. It's 128 bits total, and the architecture gives it 15 bits of the exponent and a massive 112 bits for the mantissa, or the significant.
And what does that translate to in terms of decimal digits we can actually trust?
That combination gets you approximately 34 stable decimal digits.
34 stable digits. I mean, that is a complete game changer. Let's put that in perspective. A double gives you enough precision to measure the Earth's circumference accurately to, what, a few millimeters?
Something like that, yeah.
So quad, with 34 digits, that allows you to calculate gravitational effects across the entire solar system down to the subatomic level. I mean, that's the kind of difference we're talking about here.
Then you have the octuple. This was the library, just it leaves the atmosphere.
Right.
At 256 bits total, it uses 19 bits for the exponent and a colossal 236 bits for the mantissa. And that delivers the absolute gold standard of precision, around 71 stable decimal digits.
71 digits. That's just, it's almost unimaginable. What kind of practical application truly demands 71 digits of precision? Are we talking about simulations that have to run for cosmic timescales or something?
It's often about long-term stability and avoiding what's called catastrophic cancellation. Imagine a global climate model, or maybe a molecular dynamics simulation that's running for what would be the equivalent of thousands or millions of virtual years.
So tiny errors just build and build and build.
They accumulate over time and can completely wreck your results. Or in cryptography, generating keys based on complex number theory often requires incredibly high intermediate precision just to make sure the final result is mathematically sound. When money or safety is on the line, that 71-digit guarantee absolutely justifies the complexity.
Okay, let's go back down to the 16-bit formats for a second, because that's a fascinating choice in the other direction. Half versus bfloat 16. Both are 16 bits, but they have completely different goals.
It's that classic trade-off, isn't it? Range versus precision. The standard half precision, the IE 754 binary 16, it uses 5 exponent bits and 10 mantissa bits.
So the 10 bits of mantissa means you get higher precision.
Exactly, about 3 to 4 decimal digits. But with only a 5-bit exponent, your range is really limited. You're stuck with numbers up to around plus or minus 65,504.
And bfloat 16, or brain floating point. That came out of the machine learning world, right? It flips that allocation.
It does. It uses 8 exponent bits and only 7 mantissa bits.
And the power of that 8-bit exponent is its massive range.
It's huge.
Yeah.
And this is the key. bfloat 16 has the exact same exponent range as a 32-bit float. So you get this gigantic range up to about 3.4 times 10 to the 38.
Which is perfect for neural networks where values can just spike unexpectedly. It reduces the risk of overflow or underflow.
Drastically. But you sacrifice precision. By dropping the mantissa to 7 bits, you're down to only 2 to 3 decimal digits.
So TLFloat supports both. You choose based on your constraint range for machine learning or precision for maybe graphics or audio. It's a practical choice.
And tying all 6 of these types together from 16-bit all the way to 256-bit octuple is that one non-negotiable rule we mentioned.
Full IEAC 754 compliance.
Full compliance.
And when we say full compliance, we don't just mean adding 2 numbers together correctly. We're talking about the weird stuff, the edge cases that break simple math.
Absolutely. This includes proper handling of special values like nan n not a number, which you get from undefined operations like 0 divided by 0 or infinity minus infinity.
Right.
It also means handling positive and negative infinity correctly, and crucially, sign 0. So plus 0.0 and minus 0.0. You have to make sure that dividing by a sign 0 gives you the correctly signed infinity.
And the really important one for numerical stability. Subnormal numbers. They're often called denormals.
Yes, and these are numbers that are smaller than the smallest possible normalized number.
Why is supporting them so important?
Subnormal support is what guarantees something called gradual underflow. Instead of a result just suddenly collapsing to zero when it gets too small, subnormal numbers let the system gracefully lose precision while still maintaining as much accuracy as possible all the way down to zero.
So without them, you get a big discontinuity, a big gap in your number space.
A massive one. And that guarantees instability for any kind of delicate iterative calculation. TLFloat ensures that smooth, gradual behavior across all 6 of its types.
That was a great breakdown of the architecture. But now we have to get into the absolute foundation of this high-precision world. You mentioned that an octuple has a 236-bit mantissa.
Yeah,
Anyone familiar with modern computing knows that a standard CPU is a beast at handling 64-bit integers. It's what it's built for.
exactly. You ask a CPU to add 2 64-bit numbers, it's basically instantaneous. It's a single hardware instruction.
Yeah.
But when you need to store or add or multiply numbers that are 128 bits long, 236 bits long, your hardware just throws its hands up.
It can't do it, not in one cycle.
It can't do it.
Yeah.
So if you want a floating point system that goes beyond a 64-bit double, you are forced to abandon hardware acceleration for the mantissa part of your number.
Which means the TLFloat engineers had to essentially invent their own highly optimized software-defined integer math engine.
And that's the real insight here. The entire foundation of high-precision floating point math in TLFloat rests on these arbitrary precision integer templates they created. Big N for signed numbers and Big N for unsigned. They solved the precision problem by just giving up on the hardware and betting everything on custom integer math that was designed from the ground up for speed.
So the quad and octuple types are just sitting on top of this custom Big N and Big N support layer. Tell us how they structured Big N. What does that look like under the hood?
So Big N, where n is the bit width, is designed to represent an unsigned integer less than 2 to the n. But the cleverness is how they manage these huge numbers. It's not just a flat array of bytes.
Okay.
They use a recursive binary tree structure.
A recursive binary tree for a number. That sounds pretty complex.
It is, but it's incredibly efficient for doing operations. So imagine a massive integer. Instead of storing it as one long, unwieldy string of bits, they recursively break it down into 2 parts, a high component and a low component.
So a big N is made of 2 smaller Big N on 1 parts, and that just keeps going down.
Yes, exactly. The recursion continues all the way down until they hit the base case. And the base case is defined as Big N6.
And what's that?
Big N6 is just a simple wrapper around a standard 64-bit unsigned integer, AN64T.
Ah, that is brilliant. So while the huge 236-bit octuple mantissa is managed with all this recursion, the fundamental building block is the fastest thing the CPU can possibly handle, a native 64-bit operation.
You got it. And by using recursion, they can implement these incredibly efficient divide-and-conquer algorithms for the math.
And I assume Big N for signed numbers is built on top of that.
Yes. The Big N class just wraps the Big N internally and uses 2's complement to manage the sign. It's standard practice, but it's essential for getting subtraction right with guaranteed precision.
Okay, so that's the structure. But now the real challenge, speed. Just having a way to store big numbers isn't enough. If your 256-bit addition takes a full minute, the library is useless.
Completely useless. You need advanced algorithms to keep performance reasonable. And let's focus on multiplication, because that's always the most expensive operation for these arbitrary precision integers.
Right.
For 2 numbers of length, n, the simple, school book method you learned has a time complexity that's proportional to n squared. When n gets big, like 256 bits, that n squared complexity is just devastating.
So what does TLFloat do?
It adapts. It dynamically changes its strategy based on the size of the numbers it's multiplying to use the fastest possible algorithm for that specific size.
Okay, so it has multiple strategies. Tell us about them.
For the smallest sizes, specifically when n is 7, which corresponds to 128-bit numbers, since the base case is 64 bits, they just use direct multiplication. It's the simplest, fastest method when the numbers are small enough.
And for slightly bigger numbers?
As the size increases a bit, to n equals 8 or 9, which is up to 512 bits, they switch to a loop-based multiplication method. That's often better than the direct approach once you pass a certain threshold, but it's still pretty slow for the really big numbers.
Which brings us to the high-stakes optimization.
This is it. For all the larger sizes, n greater than or equal to 10, which includes the 256-bit octuple mantissa, and anything bigger, the library uses the Karatsuba multiplication algorithm.
Karatsuba. I've heard that name before in like high-speed math contexts. Why is this algorithm so critical for making this whole thing usable?
Karatsuba is a fast multiplication algorithm that's built on that same recursive divide and conquer principle we were just talking about.
Okay.
Instead of doing the 4 submultiplications you'd normally need when you break 2 numbers into halves, Karatsuba cleverly rearranges the terms so that it only needs 3 submultiplications plus a few extra additions and subtractions.
So by reducing the number of core multiplications from 4 down to 3 and doing that recursively, what does that actually do to the complexity curve?
It completely changes the scaling behavior. Where the standard method scales by n squared, Karatsuba scales by n to the power of about 1.585.
That exponent difference doesn't sound huge, but I'm guessing it is.
Oh, it's astronomical. When you're multiplying numbers with hundreds of bits, the computational savings are just enormous. It transforms multiplication from this paralyzing bottleneck into just a merely expensive operation. It's what makes octuple precision math feasible in the first place.
That is the hallmark of brilliant engineering, picking the right tool for the right scale. So what about division? That's usually even slower than multiplication.
It is. And that's why they rely on really optimized classical methods. They implement Knuth's algorithm D for division.
Don Knuth, of course.
His work on this is just foundational for multi-precision division. It's a standard, highly refined approach. They also use reciprocal-based approximation methods, where you estimate the reciprocal first and then use multiplication to get closer and closer to the right answer. That can be faster in some cases.
So a lot of the performance comes from these smart algorithmic choices, but you also mentioned they get right down to the silicon level using platform specifics. How do those low-level intrinsics help the BigInt engine?
Okay, so think about this. When you add two 64-bit numbers and the result overflows, you get a carry bit, right?
Right.
When you're chaining multiple 64-bit words together to represent a 256-bit number, you have to handle the carry from word 1 and add it into the calculation for word 2. Standard C++ doesn't give you direct, efficient access to that carry bit.
Ah, so they use the specialized CPU instructions directly.
Exactly. They leverage architecture-specific intrinsics, like by 86 intrinsics, which expose these low-level operations for arithmetic with carry or borrow. This saves crucial instruction cycles and just makes the multi-word addition and subtraction as fast as humanly possible, right at the metal.
I also saw they use compiler built-ins for counting leaving zeros. That seemed like a minor specific thing. Why is it so important for floating point math?
Counting leading zeros is absolutely essential for the normalization step of any floating point operation.
Ah, right.
After you do a multiplication or addition, you need to know how far to shift the resulting mantissa and adjust the exponent to get it back into the standard format. A hardware instruction or a compiler built in that can count those leading zeros in a single shot saves dozens of cycles compared to doing it in a software loop.
So it's these tiny microscopic optimizations that add up.
Across billions of operations, they define whether your library is usable or just way too slow.
And one final detail about this core engine, the sources mention it's robust enough to be used in cryptography.
Yes, the BigInt implementation is so well designed that it actually includes specialized support for key cryptographic operations. They specifically mention Montgomery reduction and modular exponentiation capabilities. So the same engine that's handling your 71-digit floating point math is also capable of doing serious public key crypto. It just underscores how efficient and reliable it is for any kind of large integer operation.
Okay, so now that we understand that BigInt foundation, let's move up the stack to the actual floating point calculations. These are all orchestrated by that unpacked float template you mentioned.
Right, and the basic arithmetic addition, subtraction, multiplication, division is managed by these internal methods like FADSUB, FORMMUL, and FDiv.
But when we talk about these operations in TL float, we're not just talking about adding two numbers. We're talking about doing all those BigInt operations while following the IEEE 754 standard to the letter.
Which is like a 7-step process for any FP operation. It's really involved.
Let's use multiplication form as an example, just to illustrate the complexity required for this guaranteed accuracy.
Sure. The first step is always special case handling. Before any calculation even starts, the library checks if either of the operands is a nan, infinity, or a 0. And the rules have to be exact.
For example,
if you multiply infinity by 0, the result must be nan. If you multiply infinity by any non-zero number, the result must be infinity. All those rules have to be hard-coded and checked first.
Okay, so assuming we have two normal numbers, the next step is to use that BIGINT engine we just talked about to multiply the significance.
Correct. And that gives you this raw product mantissa that's actually twice the size of the original ones.
Then step 3 is exponent management.
Right. You add the exponents of the two numbers together, and then you have to subtract the exponent bias. If you're using octuple, for example, your bias is based on having 19 exponent bits. That calculated value becomes the preliminary exponent for your result.
And then comes the normalization step. This relies on that counting leading zeros thing we talked about.
It does. The big mantissa product is checked. If it's too large, you shift it right and increment the exponent. If it's too small, you shift it left until the leading bit is set correctly and you decrement the exponent.
And then the final critical step, rounding.
This is everything. That huge intermediate result now has to be truncated and rounded according to whatever rounding mode is specified. It's usually round to nearest even to fit back into the required precision. So 112 bits for quad or 236 bits for octuple. It's this precise final rounding step that maintains that IEEE 7504 promise.
This step-by-step adherence to the standard is what gives you confidence, and I can't think of a place where that's more crucial than in the fused multiply-add operation, or FMA. It computes A, B plus C.
FMA is the secret weapon for numerical analysts who are hunting for stability. If you do it the naive way, you calculate a B first. You get an intermediate result, and that result has to be rounded to the standard precision.
So you lose some digits right there.
You lose precision. Then you add C to that already rounded result, which introduces a second rounding error.
That's 2 opportunities for precision loss. I imagine that's disastrous in certain situations.
It's particularly bad when AB is almost exactly equal to C, but with the opposite sign. That's a classic scenario for catastrophic cancellation, where all your significant digits can just vanish.
So how does FMA solve this?
FMA performs the entire AB plus C calculation internally, using extended precision, usually double the normal mantissa size, and it performs only a single final rounding step right at the very end.
So 1 rounding error instead of 2.
Exactly, and that guarantees higher accuracy by avoiding that intermediate precision loss. It fundamentally improves the stability of complex operations, like a lot of linear algebra.
Okay, FMA handles arithmetic brilliantly. But the real challenge for any of these high-precision libraries is calculus, transcendental functions. And the library provides a huge suite of them: trigonometric, exponential, logarithmic, power functions, even special ones like gamma and error functions.
And the success criterion for these functions is, well, it's nearly impossible. They guarantee 1 ULP accuracy.
Okay, let's make sure we ground that concept. ULP unit in the last place. What does it actually mean to guarantee 1 ULP accuracy?
ULP is a way of measuring error relative to the precision of the format you're using. So if a result is 1 ULP accurate, it means the value the library computed is one of the 2 floating point numbers that are closest to the mathematically true infinite precision result.
So it's the highest possible standard of accuracy you can get in finite math.
It's the best reasonable promise a library can make. A 0.5 ULP error means you successfully rounded to the single closest number. A 1 ULP guarantee is the gold standard.
And achieving that, especially across the 71 decimal digits of octuple precision,
Yeah.
that must require techniques that go way beyond simple Taylor series expansions.
Oh, you can't use simple expansions. They're not stable enough. The core strategy, especially for trig functions like sine and cosine, is range reduction.
What does that mean?
If you ask for the sine of, say, 10 to the 50, trying to calculate that directly is just numerically unstable. The argument is so large that representing its phase accurately is impossible.
So instead of calculating sine of x directly, they reduce x to a much smaller argument.
Exactly. They find a small remainder r such that x equals 2k plus r, where k is some huge integer. They reduce the argument down to a highly predictable range, like, say, absolute value of r is less than pi over 4.
And they have to do that reduction with extreme precision itself.
Using the highest available precision with a very high precision value of pi, just to make sure that remainder r is itself accurate to within 1 ULP of the original number.
Okay, so once the argument is reduced down to something small and manageable, how do they get a 1 ULP accurate value for, say, sine of r?
They use polynomial approximations. But these are not generic polynomials. They are specifically generated minimax approximations using highly customized precision-specific coefficients that are designed to minimize the error across that small reduced range.
So an octuple calculation would use a different polynomial than a quad one.
A much more complex one. For octuple, these polynomials will have dozens of terms, and the coefficients themselves are calculated using reference math like MPFR to ensure they are exact.
The sources also highlight a technique called precision scaling. This sounds like the link between how quad and octuple are handled in these math functions.
It's the adaptive nature of it. Precision scaling just means that the higher precision types, like quad and octuple, have to use significantly more polynomial terms and sometimes extra iterative refinement steps for their intermediate calculations.
Why is that?
Because the required accuracy is just exponentially harder to maintain. If you have a 236-bit mantissa, you might need to use an intermediate working precision of maybe 300 or 400 bits just to ensure that when you round the final result back to 256 bits, you are guaranteed to be within that 1 ULP boundary.
So the cost is high, but the guarantee is absolute.
It's the difference between guessing where the boundary is and mathematically proving your final result lies on the correct side of it.
And to wrap up the math capabilities, they also provide high-precision mathematical constants like pi e natural log of 2, and they do it through const_expr functions.
Which is a fantastic feature for both performance and reliability. Using const_expr means these constants are computed with the appropriate high precision, whether you need 34 digits or 71 directly at compile time.
So there's no runtime overhead.
None. And more importantly, it removes any potential source of error from, say, initializing a constant using lower precision literal. You just get the perfect octuple pi calculated once, guaranteed.
We've established that the engineering here is incredibly sophisticated. It's resting on this custom arbitrary precision software. But in the world of numerical computing, sophistication means absolutely nothing if you can't prove it's correct.
Right. If you have one rounding error in one obscure function, the entire library's reliability is just compromised.
So correctness is the absolute priority.
It has to be. Floating point behavior is notoriously subtle, especially when you're combining software-defined math with all those IE 754 edge cases. TLFloat's reliance on a comprehensive verification framework is as much a part of the product as the code itself.
And their approach isn't just internal checks. It's systematic comparison against trusted, independent reference implementations. They have to prove that their custom software matches the world standard.
It's a triangulated approach. They rely on 3 primary reference libraries. First, for the basics, they use native FP, the hardware implementations, to verify operations on float and double. That just ensures their wrapper classes aren't adding any overhead or error.
Okay. And second, and this one is the most critical for the custom precision, is MPFR.
MPFR, which stands for Multi-Precision Floating Point Reliable, is the gold standard in arbitrary precision software. TLFloat uses MPFR as the definitive reference implementation for all of its mathematical functions across all precision types.
So if TLFloat sign of X disagrees with MPFR sign of X, TLFloat is wrong, period.
TLFloat is considered wrong. It provides that independent, mathematically rigorous baseline for comparison.
And third, they also check against libquad math for the 128-bit operations.
Right. And using libquad math lets them directly benchmark and compare, not just for correctness, but also performance, against another widely established 128-bit software implementation.
The crucial metric they use through this whole process is ULP analysis. We talked about ULP for accuracy, but here it's measuring the difference between the TLFloat result and the trusted reference result.
ULP analysis is really the only way to prove correctness in finite precision. It measures the exact distance between 2 floating point numbers in terms of how many possible representation steps there are between them.
So if the true mathematical answer lies between 2 representable numbers, A and B, a correct implementation has to return either A or B.
Exactly. So a test will typically pass if the ULP difference is less than or equal to 1.00. That means the TLFloat result is either identical to the reference or it's one of the 2 nearest representable numbers to the true value.
Which is the definition of a correctly rounded result, according to IEE 754.
And anything greater than 1.0 ULP indicates a rounding error, a bug, a failure somewhere in the calculation. Achieving that metric across millions of tests is a huge, huge hurdle.
The testing strategies they use are just as rigorous as the metric. For the smaller types, where you can actually manage the input space, they do exhaustive tests.
This is a complete brute force verification. It leaves zero uncertainty. For the 16-bit types, bfloat 16.5, they test every single one of the 2 to the 16, so 65,536 possible input bit patterns against the reference.
It's every single one.
Every one. They check the result of every addition, subtraction, multiplication for every single combination of those 65,536 inputs. That is a staggering level of assurance for those low-precision types.
But once you go past 16-bit, that approach becomes impossible. 2 to the 32 is too big, and 2 to the 2056 is just beyond comprehension.
Way beyond anything testable.
Wow.
So for the larger types, they switch to random testing.
Which lets them sample a wide range of the input space.
But reliability is still paramount. And the sources emphasize that their test generation is seeded deterministically. This is absolutely crucial.
Right, because if a test fails in a random run, you have to be able to reproduce the exact conditions of that failure to have any hope of debugging it.
Exactly. Deterministic seeding means that every random run, no matter what platform you're on or what time of day it is, uses the exact same sequence of input values. If a failure happens, the inputs are logged, and a developer can instantly recreate that scenario.
And beyond the random and exhaustive tests, they have to make sure all those special rules we discussed are handled perfectly.
So they have special case testing, explicit checks for everything, the correct behavior of NaN and infinity through chained operations, guaranteeing distinct results when you operate on sign 0, ensuring the stability of subnormal numbers near the underflow limit, and testing that all the different rounding modes are applied correctly.
And finally, cross-platform verification. The number of environments this library has to support is just enormous.
It's a huge matrix. Linux, Windows, macOS, FreeBSD, even specialized targets like WebAssembly and GPU environments like CUDA. And they use a wide range of compilers, GCC, Clang, MSVC, NVCC.
So how do they ensure consistency across all of that?
They use hash-based verification. This ensures that the identical input across every platform and compiler combination produces an identical compliant result. It prevents those subtle environment-specific bugs that are so common in this kind of low-level numerical work.
That sounds like a monumental task. What happens when a test does fail? You need good diagnostic info.
The error reporting framework is designed to that. It doesn't just say failed ULP check. It outputs the exact input values that caused the failure, the expected result from the MPFR reference, the actual TL float result, the hexadecimal binary representation of both for direct bit-level analysis, and the precise ULP difference.
That detail must cut down debugging time immensely.
Drastically. Especially when you're trying to fix a tiny precision loss somewhere in a 256-bit mantissa. It sounds like the verification process requires just as much engineering rigor as the math itself.
Okay, so we have a library that guarantees 1 ULP accuracy across an incredible precision spectrum. It's built on complex, custom integer math, and it's proven correct by this exhaustive testing. The final piece of the puzzle is accessibility. How does a user actually integrate octuple math into a real application without tearing their hair out?
That's a huge point, and TLFloat clearly prioritized maximum compatibility. They understand that these advanced numerical libraries have to play nice with legacy code, high-level languages, specialized hardware, all of it.
So they address this with multiple interface layers.
Right, all built on that same singular tested core implementation.
So what are the 3 main layers?
First, you have the modern C++ API, which is compatible with C++20. This is the cleanest interface. It leverages all the modern C++ features, templates, operator overloading, so you can just type A plus B, and constix par for those compile time constants. This is the best experience for new code.
But not everyone is on C++20.
Exactly. So second, they maintained a C++11 compatible API for backward compatibility. This gives you the same core functionality with class wrappers and overloaded operators, but supports users on older, more stabilized code bases.
And finally, the universal layer, the C API.
This is the one for universal compatibility. It uses traditional C function calls and plain old data types, like TLFloatQuad and TLFloatOctuple. This layer is absolutely essential for integration with any language that supports a C foreign function interface.
So think Python, Fortran, Java.
Any of them. You can call into TLFloat from pretty much anywhere.
And the C API uses a very systematic naming convention to keep all these precision levels straight.
It's a clear suffix system. Functions for your standard 64-bit double usually have no suffix. Functions for 32-bit float use F.
And for the extended precision types that are the focus here.
They use size-specific suffixes, so Q for quadruple, 128-bit operations. You'll see functions like TLFloatAddDQ, TLFloatMulk, or TLFloatSync.
And O for octuple, I'm guessing?
It's exactly O for the 256-bit octuple operations, like TLFloatDido or TLFloatDevo. This systematic approach is applied across everything: arithmetic, power functions, transcendentals. So it's always clear what precision you're working with.
Integration isn't just about calling functions, though. It's about getting the results out, especially when you're debugging or logging those 71 decimal digits. A standard C print isn't going to know what to do with a software-defined 256-bit float.
Correct. So the library extends the standard print functionality. You can use a bit-width modifier like %208G for quad or %256G for octuple. They also offer alternative size prefixes like %U for quad in exponential notation or %G for octuple in a general format.
And on some systems, they have an even smoother option.
Yes, on systems using glib 2.14 or newer, TLFloat can actually register hooks into the system's standard print implementation.
What does that mean for the user?
It means if you pass a TLFloat extended type to a standard print call, the system just knows how to format it correctly. It seamlessly handles quad and octuple without you having to switch to any proprietary functions. It's all about minimizing friction.
Okay, that covers usability, but now we have to face the reality check. The core trade-off we mentioned right at the start. You've convinced me that TLFloat is accurate and compliant, but all this reliance on recursive BigInt, on Karatsuba multiplication, on these complex polynomial approximations, it has to come at a performance cost.
It absolutely does. This is the critical piece of information for you, the listener. The quad, 128-bit, and octuple, 256-bit types are significantly slower than native float and double. There's just no way around it.
Why?
Because they operate entirely in software. Every single operation, every addition, every multiplication requires dozens, maybe hundreds, of underlying 64-bit hardware operations that are being orchestrated by that custom BigInt implementation.
So if a user is currently on a hardware-accelerated double and they decide to upgrade to a TLFloat quad, what kind of slowdown are we talking about qualitatively?
A native double operation might take one CPU cycle. A quad operation might take dozens of cycles. An octuple operation, especially for a transcendental function, could take hundreds. The performance difference is stark.
But the sources do provide benchmarks comparing TLFloat quad against other software implementations, right? Specifically libquadmath.
They do. And this is where TLFloat's optimized engineering really shines, even within the tight constraints of software math.
So how does it stack up?
For basic operations, TLFloat often outperforms the competition. For instance, the Quad Edition benchmarks show TLFloat hitting about 124 million operations per second, which significantly beats libquadmath's 87 million.
And multiplication.
Similar story, about 102 MOPS for TLFloat quad versus 78 for the reference.
And what about that fused multiply-out operation, the critical high-accuracy one? The benchmarks there showed a massive difference.
An incredible difference. TLFloat quad FMA runs at 68 million operations per second. The reference implementation only manages 1.9. That difference just underscores the value of TLFloat's highly optimized, single-rounding FMA implementation.
That's really impressive. It demonstrates superior engineering in software. But let's bring the challenge back. Where is the performance bottleneck, even for TLFloat?
The bottleneck is clearly identified in the benchmarks. It's division, square root, and all the transcendental functions, sine, cosine, log, power. These operations require complex, iterative BigInt computations, and they are inherently the slowest.
Can we quantify that slowdown?
We can. For example, in the benchmarks, TLFloat quad division runs at about 50 million operations per second. This is still fast, but notably, libquadmath is actually faster here at 72 million.
Interesting.
It clearly shows that the iterative complex logic you need for a guaranteed 1 ULP division is where software math just hits its limits no matter which library you're using. They simply have to spend more cycles to ensure that perfect rounding.
So the engineering is fantastic, but the laws of algorithmic complexity still apply. What's the practical optimization advice for a listener who's planning to use quad or octuple?
The advice is twofold and absolute. First, always choose the minimum required precision. If double works, use double. If quad gives you 34 digits and that's enough, do not upgrade to octuple just because you can. The performance cost scales dramatically with bit width.
And second?
Second, choose algorithms that minimize expensive operations. If you can, restructure your calculations to use addition and FMA rather than relying heavily on division, square root, or transcendental functions. This kind of disciplined approach is absolutely essential for keeping high-precision software math usable in the real world.
That really brings the whole project together. It places the numerical burden squarely back on the application's design. TLFloat gives you the tools for guaranteed precision, but you, the user, have to pay that performance tax very, very judiciously.
Precisely. It forces that necessary critical assessment of whether the risk of numerical error from native hardware truly justifies the cost of custom software precision.
That was an incredible deep dive into the engine room of high-accuracy mathematics. What we've seen is just a masterful piece of numerical engineering in TLFloat. They have successfully bridged this enormous gap between the raw speed of native hardware floating point types, and the extreme precision needed for these specialized fields advanced scientific simulation, finance, cryptography.
The achievement really is profound because it's not just about having bigger numbers, it's about the guarantee. They deliver the gold standard of IE 754 compliance, including subnormal numbers, special case handling, across 6 distinct precision levels. And they prove it, through exhaustive testing, that their Cufton 256-bit software math maintains 1 ULP accuracy across 71 decimal digits.
But this entire discussion has really illuminated that constant, difficult negotiation that's inherent in numerical computing. You always have to decide where your priority lies.
And that's what I want to leave you with. This final provocative thought to mull over. If achieving 1 ULP accuracy across 71 decimal digits requires implementing complex, recursive integer arithmetic and demonstrably slows down your execution time by multiple orders of magnitude compared to just using hardware, how do we, as numerical problem solvers, truly decide which specific application warrants the expense, the CPU cycles, the power, the time of perfect numerical precision, and which application can safely tolerate the risk of a slight, tiny error for the massive, overwhelming gain in processing speed that the hardware provides? That negotiation precision versus performance is the constant fundamental challenge in modern computation. And now you know the cost of the ultimate solution.